Hello and welcome. This is Noah, and in this video we are going to look at doing some absolute value functions. We just want to do an introduction with an application, give you an idea of what an absolute value function is and how it gets used sometimes. So the example we're going to look at is in manufacturing. The error between a design specification and the piece that is actually produced must always be within a certain tolerance. For example, when a drink company fills a 12-ounce bottle, there will often be a tolerance of 1/2 ounce. As long as there are between 11.5 and 12.5 ounces in the bottle once it's filled, it's considered fine. If it's under or overfilled, they will discard it. We can use the function capital E of capital V equals the absolute value of capital V minus 12, close absolute value, takes the actual volume of liquid in the bottle, capital V, and outputs the error, capital E, between the actual volume and the intended volume of 12 ounces. Note that this error is always considered a positive number and doesn't worry about whether the bottle was overfilled or underfilled. Instead, it only tells us if the error is better or worse than it is supposed to be. Okay, so we could take the actual volume, capital V, and subtract 12, and say we had 12.3 ounces in the bottle, and we subtracted 12, and we say, okay, we have 0.3 left over. Let me write and not just talk here. If the actual volume, capital V, is 12.3, then the error is 12.3 minus 12 equals 0.3, right? In that case, it's already positive. We don't have to worry about any negative. If the actual volume, once the machine fills up the bottle, if it ends up being like 11.8 ounces, say, then the error is 0.2 ounces, right? It's supposed to be 12 ounces, and it's 0.2 off. We always think of error as just how much it's off. We always think of it as a positive value. We never talk about whether it's a negative or positive error in that manner. We can say, is it overfilled or underfilled? Like, when we look at the error, can we say, is it too much or too little? We can have that conversation. But error by itself, we just say, by how much is it off? So if I did 11.8 minus 12, this would give us a negative 0.2. And so to adjust for that, we would say that the error equals a positive 0.2 already, but that's the absolute value of the 11.8 minus the 12. So while it's possible to do the subtraction first and then say, well, the error is just the positive version of that number, that actually is taking the absolute value after we've done subtraction. Like we say, what is the absolute value? It is to say, just look at the positive version of that number. That's when we use an absolute value function, is when whatever subtraction we're doing, we only care to think of the answer as positive, to look at the positive difference between two values. So we're going to do a couple of things with this as we wrap our heads around what an absolute value function is and how and when we use them. We're going to create a table of values around V equals 12, going by 0.25, and then we're going to graph E of V using this data. I'm realizing I need some rule lines on my screen today. So I'm going to make a table here. We have V, we want E of V, and we'll do the graph in a second. So we'll go, let's say 11, 11.25, 11.5, 11.75, 12, 12.25, 12.5, 12.75, and all the way to 13. I'm going to do this two ways. First, if we know that the volume is supposed to be 12 and we have a volume of 11, the error is 1, right? If I have a volume of 11.25 when it's supposed to be 12, we know that the error is 0.75, and the units here is ounces. If I use the absolute value function, I could say, what is the error of 11.25? Using the absolute value notation, we would say that this equals the absolute value of 11.25 minus 12. And then I do inside the absolute values first to get 11.25 minus 12 is negative 0.75. And then the absolute value of that, just the positive version of it, is 0.75. I'll do this one more time. If I have the error of 11.5, this would be the absolute value of 11.5 minus 12, which equals negative 0.5, and then take the absolute value to get a positive 0.5. And I can put that in the table. So we could do this by hand, or rather plug it into the function over and over again. But we can also just take the difference and think of it as positive. So the difference between 11.75 and 12 is 0.25. The difference between 12 and 12 is 0, so if it fills up to exactly 12 ounces, we have a 0 error. If it fills to 12.25 ounces, we have a positive 0.25 error again. If it fills to 12.5, our error is 0.5. If it fills to 12.75, our error is 0.75. And if it fills to 13, our error is 1 again. Right. Let's get coordinate plane drawn, and we'll graph this. So our horizontal axis is the input. That's our volume, capital V. That's V, that's volume in ounces. And the vertical axis is capital E. That's error. The error is also in ounces. All right, let's plot some points here. Our volume really needs to be looking out at 12, so I'm actually going to move this a bit. Let's take this line. Come on, let me select it. There you go. Oh, I want to select this too. Move this over here. Cool. And then I'm going to say, oh, where do we want to put 12? Sorry, fighting with the software here. Oh. Like we need to go by 0.25 on one hand, and on the other hand, I need to get all the way out to 12. So I'm trying to consider how best can I do this. There is a bit of a way around this, but I don't think I want to use it today. So what if I just go and say that here's 1, so that these are each worth 1/2. So then I have 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 is all the way out here. So I will continue this to the right a little bit farther for all of the language buffs out here. All right, so 12, let's move this. Is going to be, here's 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. That's fine. And so if we're at 11, the error is 1. I'm going to put 1 right here. From an 11, the error is a 1. If I'm at, let's just do 11.5, the error is 0.5. If I'm at 12, the error is 0. At 12.5, the error is 0.5. At 13, the error is 1 again. If I was at 14, the error would be at 2. If I was at 10, the error would also be at 2. So we get this V shape out of this. I'm going to label a couple of these. Here's 12.5, comma 0.5. Over here we have 11.5, comma 0.5. And then I have 13, comma 1 and 11, comma 1. So if I draw this, it's a straight line through these points to the right of 12, and then another straight line over here to the left, coming down towards 12. And we get a V shape out of this. And this V shape is the graph of E of V, right? Error is the outputs of this line, and the V is the inputs. Note that this graph never goes negative. It has no negative error values because we're always taking the absolute value. And whatever we plug in after we do the subtraction, we always make it positive afterwards. So if we're going to discuss how the inputs and outputs are behaving, we could say as the volume, the inputs, is less than 12, but approaching 12, the error, the outputs, are decreasing. As the volume goes past 12, the error hits 0 at 12 specifically, and then goes up. Right? After we go past 12, the error starts increasing again. All right, the next thing for part C, in fact, I'm going to change that color that way. All right, so for part C, I'm going to do this in red. It says graph that capital E equals 0.5, and note how the volumes between 11.5 and 12.5 ounces are related to keep the error less than 0.5. So there's nothing surprising here, I don't think, but let's just take a look at what this is trying to say. I'm going to graph, it's a horizontal line along where the error is 0.5. So I just draw a horizontal line at the at the 0.5 error level. This is the line E equals 0.5. This crosses our error function at 11.5, comma 0.5 and at 12.5, comma 0.5. So when the volume is between 11.5 and 12.5, the error is less than, the error function is the V shape, it is then less than 0.5. Another way to write this, copy this down here as well. chatting with the software. Let's just move this down here. Another way to write this is when 11.5 is less than or equal to v is less than or equal to 12.5, then the error, capital E, is between 0 and 0.5, right? It's not anything less than 0.5. It's never smaller than 0, so we can say that it's between 0 and 0.5 there. All right. So this is just our introduction, but that ends this introduction. Go ahead and go back to the mind map. Click on Now You Try. Look at those 3 little bars at the new Now You Try problem on the mind map. That'll show you the problem to look at, and go ahead and try on your own before watching the next video when we walk through it. Thanks much. See you in the next one.